Thank you very much, and thanks also for having me here. So I'd like to talk about capturing 3D models. I think in possibly some of the other talks, we hear a lot about neural radiance fields, which are very cool, but I do think we do still need actually 3D models in order to be able to capture proper interactions and 3D consistent effects across views. So in particular, all right, sorry. What I'm interested in is capturing geometric material models of these kinds of real world environments around us with just commodity sensors. So a cell phone camera, maybe an iPhone with LiDAR, and being able to understand the structures of the objects and how they're being organized in a scene. So this has applications, of course, to things like robotics, being able to move around and navigate in a scene and in an environment and understand what the objects are, as well as for things like content creation, mixed reality, being able to get interactions between virtual objects and real scenes. So I started working in this on real-time 3D reconstruction. So from some kind of RGBD sensor like the Microsoft Kinect, where we get a real-time color stream and depth stream, we can optimize for the camera poses of these observations in order to get some kind of 3D model of the scene that represents what's being observed. So with that, we could do a real-time scanning where somebody can walk around, actually observe an environment, see what the reconstruction actually looks like so far, and continue to use that in the feedback loop to scan these kinds of scenes with just some kind of Kinect or iPad kind of sensor. And you get out some fairly nice kind of reconstructions. For instance, like this one, which you can see basically all of the object structures, the room layout, and so on from this nice top-down kind of view. But what typically happens in practice, because we have these kinds of fairly complex scenes with so many objects inside them, is that you end up missing a lot of geometry. And the scans are incomplete. So that's because of these self-occlusions. It's because some places are more difficult to observe with a physical kind of sensor. And this doesn't fly for many of these kinds of applications because we need to be able to know where all of the geometric structures are in order to understand where there might be things like collisions or complete object structures. And so what we want to do is to understand if you observe a scene like this, we know that these are actually chairs, despite that they're actually quite partially observed. So of course, we want to be able to learn that kind of prior from data. And in particular, I think it's important to do this in a self-supervised fashion so we can actually learn on real data rather than having to rely on synthetic scenes, which are fairly different in terms of their geometric characteristics from real world kind of environments. But of course, the challenge here is all of our real captured scans are incomplete. So how can we formulate in a self-supervised kind of way so that we can learn from these sort of imperfect real world data? So these scans are composed of a series of RGBD frames where we can reconstruct a target scan. This is from the Matterport dataset. And since they're composed of a set of depth frames, we can actually just remove some of them arbitrarily in order to create a less complete version of that particular scene. So we get this correlation between less complete and more complete in terms of the input and the target that tells us about how geometry could be produced in order to reconstruct a complete version of a scene. However, in the target, you see that there are actually holes where there's typically occlusions between objects. And we know about these regions because we know from which position the camera has actually observed them. So we know which regions have been unobserved, actually. And we want to ignore these signals in the loss formulation here, where we go from input to target in this kind of way. so that we don't learn to generate anything where we don't actually know whether there's surface or whether there's empty space there. And then in order to be able to actually generate fairly high resolution scenes, we have a sparse generative network that allows us to go to this resolution here of 2 centimeter voxels as a sparse truncated sign distance field. So here we have a bunch of sparse convolutional encoders that operate on the input scan geometry. But what we want to do is to predict more structure in the complete scene than exists actually in the input. So we can't rely on the input geometry for the sparse structures for the convolutions. And so we generate this in a coarse-defined fashion, predicting a very coarse resolution dense grid first in order to estimate where we should actually apply the sparse convolutions in order to predict continually higher resolution geometry. And finally, an output TSDF representation of the output scene that you see here. And so this allows us to generate complete geometry very efficiently at fairly high resolutions. So you can see from this input scan here, we can predict a complete version of this particular scene that can actually be more complete in some regions than the target that was observed originally, where there are some holes in these occluded regions. And so that's the cool part about this self-supervised formulation, is that from a set of incomplete trained scenes, we can actually learn to these geometric patterns of structural completion that allow us to generate output complete scenes that can be more complete than any one particular scan that we've seen during training. So quantitatively, we can also measure the performance here. Of course, for something like Poisson surface reconstruction that's doing a local optimization, there's no knowledge of global structures. And so that doesn't perform very well for this kind of completion task. And these other works here are leveraging sort of dense voxel grid representations without any self-supervision, so relying on training from synthetic data, and that we can improve with our sparse generative network that can be trained in a self-supervised fashion. So what's particularly interesting, I think, here is to take a look at the self-supervision formulation. So of course, we can go from input to target scan without considering any of these notion of unobserved space. And if you do that, you end up predicting kind of scene geometry that has holes in regions where often there would be some kind of occlusion between objects. Whereas if we actually take that into consideration, we can end up getting fairly complete geometry, even in these regions that are not necessarily commonly seen. And so here we see that, well, these scans are from Matterport. The target scans are fairly complete that we're using for training. But we can take a look at what the level of completeness is required actually in order to train this kind of formulation. So here we have a scenario. This is the default scenario where we take 50% of the frames for an input scan and all of the frames available for target during training. And then we can just reduce this down to 40% for input and 60% for target, or 30% for input and 50% for target. And we maintain a fair amount of robustness towards this fairly dramatic decrease in terms of completeness for the train scans here that you see in terms of the reconstruction quality. So we can actually leverage this kind of formulation to learn from fairly incomplete set of scans here. But of course, here we've only been talking about geometry, but we do have also the RGB channel in the observations here. And we want to be able to produce sort of colored reconstructions that can be consumed visually and representing also the color observations that have been seen. So in fact, we want to go from some kind of incomplete observation and predict the complete geometry as well as color in that environment. So of course we can go back to this formulation and add in a color channel as output, but this doesn't work particularly well. So this notion of training on just the colors in terms of a reconstruction loss. We see that a lot in terms of image generation. It tends towards some kind of average or median, depending on whether you use an L1 or L2 loss, and both the average and the median are some kind of beige brown due to the large quantity of walls and floors that we have in this data set. And it's hard to use actually an adversarial loss or something like this because the target scans are incomplete. And so we don't want to learn the wrong patterns from incomplete targets in some kind of adversarial distribution. So we instead move towards the 2D domain, where actually the frames that we have observed, they're complete within their own view. And so we can then compare rendered, differentiably rendered images from our 3D scene predictions and compare them in the 2D domain and guide them basically by the RGB frames that have been observed. So here we have basically an L1 reconstruction loss in order to ground the predictions. You can see this very much tends towards like brown and beige in terms of the walls and floors. And now we can add a perceptual loss with respect to the color images, and you start to get back some finer scale detail in the output generation. And then with an adversarial loss, we get back some of the color distribution that matches the original color that's being observed. And then finally, when we combine them all together, we can actually get a nice colored reconstruction of the input observed scene. And so we can measure the FID score in terms of the color generation here. And this can improve upon state-of-the-art alternatives that are leveraging these kinds of neural field representations. And here we're just predicting basically on the direct surface, on the voxels on the surface. So here you can see some of the comparisons qualitatively where we can get back some of the color distribution and details here in the scene. Of course, it is still at a 2 centimeter voxel resolution, so that's not quite photorealistic, but we do understand a nice kind of colored structure of what's being observed here in the environments. So here we've started from RGBD data, and that, well, we do have some LiDAR sensors on iPhones. Of course, RGB images are far more easy to capture, and there are a lot more of them that are available. So can we actually understand 3D if we take away the signal of the depth frames? So from just 2D image observations, how can we understand the object structures that are being seen? And so, of course, this is a fairly under-constrained problem. So I want to take a look at this from a fairly strong 3D prior, which is to basically take a database of 3D objects and use them as a basis in order to retrieve and align the most similar model to the scene so that we can understand the structure of all of the objects that are being seen in the image. And so what we have here is basically from an input image, we leverage a strong 2D background in order to do instance segmentation. And now we have detected objects from RGB images that are embedded into a joint embedding space with 3D shapes. And here we want this embedding space to be constructed such that objects that are semantically or structurally similar to each other end up close to each other despite the different domains that they might come from. And then we also want to align the objects to the image. So we optimize for also the pose of that particular object so that it can align to the observation in the image. So here we have an RGB input. We detect a region of interest for every object and also their mask. And this is being combined together to get the feature representation for the image domain. And then we have a similar kind of processing for the 3D domain where we actually render views of the 3D shapes in order to get, in order to be able to use an analogously structured encoder similar to the RGB inputs. And so the embedding space is being constructed here with a contrastive loss that pulls together shapes that should correspond and pushes away those ones that are more different. And then we solve also for the object rotation as a quaternion classification followed by a regression refinement, and the center of the object as an offset from the estimated bounding box. So with just this kind of retrieval approach, we can actually get fairly reliable reconstructions here on the Pix3D data set. So here, this is measuring mesh AP in terms of the reconstruction quality at thresholds of 50, 75, and then in the range of 50 plus. And in comparison to mesh RCNN, which was quite popular in terms of establishing this particular task of understanding object geometry from images, our just retrieval-based approach can actually perform a better reconstruction. And here you can see the retrieval results allow for sort of valid understanding of 3D object geometry up until the database fidelity, whereas the generative model has potentially the flexibility to learn physically unrealistic kind of possibilities, especially where you have challenging things like occlusions in the scene, or some sort of small thin structures that are difficult to represent. And so the other part that is pretty nice about actually using this retrieval approach in the embedding space is that if we actually can get more CAD models at any point in time, then we can just simply embed the extra shapes into the embedding space. And that means we have a larger diversity and variety of objects that can be potentially retrieved. And we can leverage this for improved performance without having to retrain the embedding space construction. So you can see the embedding spaces that we learned here have this property where we have similarly structured objects like these round tables, despite that they're coming from these different kind of image or shape domains. And in contrast, these sort of bookshelves are clustered together in a different region in space here. So that allows us to get this notion of 3D shape and structure from an image. But what about actually understanding the object materials and textures? So here, we want to be able to also model what's being observed in potentially any kind of image observation. But in 3D, actually, well, we have a lot of shapes that might be available as examples. We don't really have very realistic kind of textures in data sets like ShapeNet that provide lots of different geometric models of shapes, whereas actually there is a lot of image data that provides photorealistic visuals of basically arbitrary objects. And so we want to look to this kind of realistic image data in order to learn to generate textures that are complex and they look realistic. So here we want to learn a 3D texture generator. So given an input shape geometry, we want to be able to learn to generate arbitrary textures on top of that geometry just by sampling different codes from a latent space. So here we want to be able to take, for instance, this chair or the car and just generate different textures well, as we move through the space of latent texture styles. So in order to achieve this, we take the input shape and condition on the input shape structure as the texture should be corresponding to the input geometry. And then we take a StyleGAN inspired kind of decoder approach in order to predict the final output textures. So in order to be able to learn from these realistic images, we then differentially rasterize the output textured shape into a bunch of rendered views, and we can compare them to the real image distribution with an adversarial formulation here. So what we wanted to do here in particular was actually to generate the textures directly on the surface of the shape, similar to how they are used in sort of many different kind of production application scenarios. So we generate the textures directly on the mesh surface as basically colors on each mesh face. So here we can develop these kinds of face convolutions that operate on mesh faces, as well as pooling operations so that we can get coarse defined hierarchies in our encoder and decoder that operate actually on these mesh faces. And so this we can adapt directly in order to predict colors for every face on the mesh. So here we have a bunch of the views being rendered now from the mesh faces, and we compare them with the real images. In particular, the data that we have from real images, we can't assume that we have multiple observations per object instance. And so we want to make sure that we also get this notion of global consistency from different views in our generated shapes. And in order to do this, we take the rendered views and we sample patches from multiple different views of the output shape that we generate, the output textured shape that we generate. And then we take a bunch of patches from the real image, in this case, just the one view, since we don't necessarily have any other views of that particular object. And we compare these ones as well in an adversarial formulation, whether they belong to the same object. And so this allows us to get a notion of global consistency across different views in our texture generation. So what does this look like? Here we have a bunch of examples of how to do texture generation. In particular, the last two with stars, these were formulated as originally as just entirely conditional generative approaches. So we've adapted them in order to be able to do texture generation. And here we're comparing against a bunch of different interesting alternatives. So we have something that's basically Pygan inspired. SPSG is the voxel-based approach to generating colors. The UV baseline is kind of a natural one, since textures are mapped into the UV space, although there are lots of discontinuities then on the surface of the shapes. And then we also have things like a texture field representation with just a neural field to generate colors in space. And our approach can generate very detailed and interesting kind of textures on these chairs in comparison to these kinds of different alternatives. So we can also train this on cars and generate colors and textures for cars. And so here you can see that this kind of approach to generate the textures on the mesh surface can provide more detailed, more realistic kind of texturing. Although you also see that basically we don't have a model here of lighting. And so you'll see that sometimes lighting will get baked directly into the color model onto the car, since all of the real world images that we're learning from have all of these kinds of environmental effects and reflections in the car windows and the car bodies. So our latent style space, we can move through it and see the different kinds of colors and textures that you get for a given particular object shape. And the nice thing here is that we see that these styles, these codes, they're consistent in some sense of texture style across different kinds of shape geometries. So we pick one particular style for these particular chairs. They end up with all the same kind of style of texturing in this example here. So with that, I just want to touch upon a couple of things that I think are still very much interesting in this particular area, which is to say that we've done a lot of stuff that looks at scenes and then takes a bit of an object-centric approach. But when I'm still think it needs to be sort of merged together in order to holistically understand all of the scene structures, objects, and layout in terms of environments, and that can potentially move us a little bit more towards something that's more generally applicable in the wild. And also, of course, what some of the other people have touched upon, I think, is that a lot of scenes here, basically, they're not purely static. So we need to be able to understand 4D dynamics, motion, how objects can actually deform and interact with other objects and the environment. And so, of course, understanding also the geometric structures, materials, and textures of moving objects in these environments is an important thing to be able to truly do some kind of notion of commodity content creation. So with that, I'd like to conclude and to also thank my students and collaborators who've done all the hard work on these projects. And I'm happy to also take some questions.